7, and I asked you guys to start working on the numbers 1 through 22, and then worksheet 1. So let's start with some questions from that stuff, if there are any. Josie?
Can you please do number 19 on the problem?
Sure. All right, let's grab this. All right, so 19, the directions here ask to solve the triangle if possible. So just, we're going to have to make sure that we're being careful because it's possible that like no triangle is possible kind of thing. So I'm going to start by drawing and labeling a picture to kind of figure out what's going on. So ABC. So what situation are we in here? That's correct. So here we should be using the law of cosines. Using the law of cosines, the only thing that we have enough information to solve for is that side C. So I will say that C squared is equal to A squared plus B squared minus 2 times A times B times cosine of angle C. So to get C by itself, just square root both sides. So I'm going to save myself some writing by just erasing the squared and sliding the square root symbol in there. Josie, so far so good?
Yes.
Okay. As I type this in, what mode should my calculator be in? Degree. How do I know degree mode? Because the angles are given in degrees. Excellent. So that was 1882. So far, so good. Okay. So now I know an angle and its opposite side, so the law of sines is now available to me, right? And I really have enough information to solve for either angle A or angle B right now immediately. Now I want to be careful here though, because right now technically I'd be in an SSA situation in both counts. So I want to make sure that when I choose which one I solve for, I can avoid any 0, 1, or 2 triangle situation. Okay with that? Now, the way that we can guarantee to avoid that when using the law of sines is choose to solve for the smaller of the 2 angles first. So in this case, choosing between angle A and or angle B, which is the smaller? Good. How do you know angle A is the smaller? Because the side opposite angle A is the shorter. Perfect. So I'm going to write then my law of sines. I'll do sine of C over side C equals sine of angle A over side A. Looking good, Jose? Okay. We'll cross multiply. We'll divide by 1882. And then we'll do the sine inverse to both sides. So sine inverse, fraction, 10 times sine 87, divided by my previous answer. So there I get 3204 degrees. Could go there. And now, since I know two of the three angles, God bless you, it's quite easy to solve for angle B. So 60.96. And there's all she wrote. Yep. So again, the big thing here, the place where we could make a mistake is if you tried to solve for the other angle and you stumbled into the bad side angle side situation. It doesn't, not every time do you stumble in there, but in this case, I think if you had tried to solve for angle B first, that would be the bad situation because you have an acute angle and the shorter side is, oh no, I guess it would have probably been fine. Maybe that would have been fine. Anyways, it doesn't really matter, but just do it the way that we've told you and you're guaranteed to not get into trouble. You know what I mean?
Yes.
Not that every time it's going to, if you don't do it one time, it might work out. It might be fine. But no, I don't want to run that risk if I'm you.
Yeah.
You know what I mean? Serge.
Just generally, so you might use law of cosine
To start.
and then use law of sine that's the smallest. Would you use law of cosine, would that be the bigger one?
Mm-hmm.
Okay.
Yeah, so if you want to use law of cosines a second time, then instead of solving for angle A, you'd want to solve for angle B to start. Now, I prefer to use the law of sines because it's a smaller form and there's less algebra to deal with. But you could use the law of cosines there. You just want to make sure you did the bigger in that instance.
Maybe it's so because there's sometimes the law of cosine would be easier to avoid the side.
Not really. You still have to make the same. You still have to be careful in the same way. I think here it ends up being okay because C is the biggest angle and side C is the biggest side. So if you're using that in the law of sines, you're always going to be in the one triangle situation. So I think on this problem, either way you would have done it, I think it would have been okay. But, if I'm you, I'm not, I don't want to mess around with having to be that careful. I just would do it the one way that I'm guaranteed to not have to think too hard about it. You know what I mean?
Yeah.
Who's next? Happy to do some more if we got some more. Tay? Yeah. So the directions for 11 are a little bit different. So in 11, it tells us explicitly that two triangles are possible, and we're supposed to solve for both of them. So I'm not going to do really any analysis to start because we've already been told we're in a two triangle situation, right? So I'll just make a place to record my work. And I'm going to use, so this means that we're going to be looking for angles B, angle C, and side C. So I'm going to use subscripts on those to differentiate them between the two different triangles. Nothing new from what we've done. And then I'll just make a spot for me to do my work for triangle 1 and triangle 2, just so I don't get confused and use the wrong measurements in the wrong situation. Now, typically, I like to do all of triangle 1 first and then do all of triangle 2 second, rather than jumping back and forth between them. You could jump back and forth between them, but I think it just makes it easier to like goof up which measurement goes with what triangle. So I'm always going to do mine just all triangle 1 and then do all triangle 2 after. All right, so starting off, I notice that I have both angle A and side A, so I can start my law of sines using sine of angle A over side A equals, and then here I know the side length for B, so I'll write sine of angle B1 over side B. Oops, side B is 17. And then we'll go ahead and cross multiply. So that gives me 16 sine B1 equals 17 sine 64. I divide both sides by 16. And then do the sine inverse to both sides. So when I go type this into my calculator, I get 7274. And now that I have angles A and B, it's really easy to find angle C. So that's 4326. And now that I have angles, oh, I guess I should record some of this stuff, huh? Take a break and do that real quick before I get too far down this rabbit hole. Okay. And now that I know one of either angle C1 or side C1, I can use the law of sines to solve for the other part. So again, sine of angle A over A is equal to sine of angle C1 over side C1. And cross multiply. And divide by sine 64. So I get 12.20-ish. So far, so good, Tay? Okay. So when I do triangle 2, something that we did yesterday, but I probably didn't emphasize hard enough. So the order that I solve the parts in triangle 1, I have to use the same order when solving the parts in triangle 2. Okay, so since I solve for angle B first in triangle 1, that means the first thing I need to find in triangle 2 is also angle B. And I do that by just finding the supplement of B1. Now, if you tried to find the supplement of angle C1, you will get the wrong answer. So it's really important that you're using the correct order there. So 107.26. And then what I found next was angle C1, so I'll be finding angle C2 next. And that's easy because, well, now I know 2 of the 3 angles. So I get 874. And now I can find side C2 the exact same way that I did in the first triangle, except obviously I'm using angle C2 instead of angle C1. And I'm going to skip the writing out all the algebra there and just write what I'm typing into my calculator because, well, it's the exact same work as the previous problem, right? So it doesn't seem like probably I need to write that all out again. And I would say for you guys, the same would be true on a test or quiz. If you write the initial equation, then what you're typing in your calculator, that's fine amount of work shown. You don't need to show all the algebra in between if you don't want to. Obviously, you're welcome to, but if you just did like this and this, that's fine. You don't have to show like this intermediate step or whatever. You know what I mean? I forgot what that number was, 271. Okay, so 107.26. I got too far down the road without writing anything. 874, and then 271, was that it? Yeah, okay, good. I guess I'll leave it here. Does that feel good, Tay? So the place where the most common mistake would be made here is if you found C2 before you found B2. That's the most common place where you could have mucked this up. Eddie?
Can I go to IT real quick?
Mm-hmm. Sure. But in general, like, just long, right? Nothing super complicated going on here. It's just kind of long. Serge?
I just have a general question again.
Yeah, go ahead, bro.
Is dividing by like sign the same thing as multiplying by the reciprocal sign? Not reciprocal, multiplying by the inverse?
No. That'd be like saying dividing by plus symbol is the same as like subtracting both sides. Like sign is an operation, right? So you undo the operation with its inverse. So like if you're undoing addition, you use subtraction. If you're undoing multiplication, use division. If you're undoing a exponent, use a radical. If you're undoing a trig function, use its inverse trig function. It's not multiplying by the inverse. It's like doing the inverse to both sides, like where we square root both sides. Does that feel okay?
Yeah, I just like I'm confused like when you divide by like sign. Like,
Never.
I'll show you.
I can divide by sign of a number.
Yeah.
Because sign of a number is just a number, right? Like here I have C1 times sine 64.
Yeah, that's what
Sine
okay.
64 is a decimal. It's the same
Yeah.
thing as like 0.754 times
Okay.
C1. So I can divide
Okay.
by 0.794.
Okay, that's why like here I was like looking like I just got confused like when you would divide by like what you did up there, and then when you would do like the inverse. Like here,
Well, what's inside of my sine?
the variable,
What's inside of my sine?
the degree.
A number. So that's the difference.
Okay, so when you have a variable in it, that's when you did the inverse.
Yep.
Okay.
Because you're just trying to get rid of the sign altogether, right? Not get rid of that number. You know. Who's next? Happy to do more if there's any more. God bless you. You're welcome. Jacob.
I have like a general question. When it says solve a triangle if possible,
Mhm.
that's just saying like do the first part where you find out how many triangles there are, and if there's 0 triangles, and it's just like undefined.
Yeah, you're just done. There's nothing to do. If there's 0 triangles, you can't solve it. But what it's telling you is that you definitely need to make sure you're checking if you can do the problem before you start just bulldozing in and doing the problem. It's saying that like some of these might not work, so you better check first. You know what I mean?
Yeah.
It's just for direction. Okay. One quick thing that I'll have to say, do you guys all feel good about telling the difference between all the different SSA cases? So there's really only, depending on how you want to organize things, there's really only 2 things that can happen. So if the given angle is greater than or equal to 90 degrees, and the side opposite the given angle is the bigger side, then one triangle is possible. Otherwise, there's 0 triangles possible. So for right triangles or obtuse triangles, it's just 0 or 1 are the only 2 possibilities. You just have to make sure the side opposite our given angle is the biggest. That's all you need to check. If it's not the biggest, it's none. If it is the biggest, it's 1. The other scenario, if the given angle is acute and the side opposite the given angle is the smallest side, then that's the 0, 1, or 2 triangles. So you have to do a little bit more work there to figure out which one that is. But any other situation, there's just 1 triangle possible. Which is probably a little easier to remember than like all the cases with the AB greater than BC stuff, because Lord knows on some of these problems the things aren't named ABC, so you have to like, okay, this is PQR, so I have to rename this so it's ABC, and then I have to go back and like make sure I named it the right A, like put the A with the right one, so I get AB and BC as the two sides I know, and it just becomes like a gigantic hassle. Thinking about it this way is probably a little bit easier because we've just defined things as like opposite the given angle on the side opposite it. You know, it just so it contains the same information. We've just kind of like summarized it in a way that's convenient to use, which is, again, if I'm a student, the first thing I do when I get some highly technical rule is like, okay, is this the form that I really want to use it with? If it's like, boy, this is kind of a hassle to use in actually doing the problems, like how can I summarize this in a way that's really practical for me, which is kind of what I've tried to do here for you. But this would be a normal thing that you'd want to do as a student, particularly in a math class. Like, okay, that's the formal definition. Yippity-yay-hoo. I'm not like doing a proof here with this. I'm just like solving problems. So like, what does this really mean for me? Like, how can I use this practically? Which is what we're doing here. You know, just kind of rephrasing it so it's a little bit easier. Does that make sense? Cool. Last chance on questions then for you guys. Alrighty then. On to section 7.4. We're going to talk about areas of triangles. So if we think back to our, well, let's just say we have just some arbitrary triangle with vertices A, B, and C and sides A, B, and C. If you go back to your geometry class, what was the formula that we used to find the area of a triangle? Go ahead. So usually we phrase as 1/2 base times height, because a triangle doesn't have a length and a width, but great. So let's say we just have an arbitrary triangle like this. What's the base and the height? Elvis? Are you raising your hand? Okay, so we can say that B is the base, sure.
And the height is the distance from the angle B to.
Yeah. So our height then would be that perpendicular line from angle B down to side B. Now, what's the problem with this if we just have an arbitrary triangle? H isn't one of the sides, right? Do we have so like that's kind of a hassle. If we have a solved triangle, or just a triangle where we know a little bit of information we can solve and get all the sides and angle measures, but then what do we do with H? Now keep in mind in your geometry class that there's nothing special about this side B having to be the base. Right? You could have picked side C as the base, in which case then like that's the height. Or you could have picked side A as the base, in which case like that's the height. Everybody cool with that? So what we're going to try to do here is we're going to try to come up with a new version of this old area formula that doesn't use height, that just uses side lengths and angle measures that we would have if we had feasibly solved this right triangle. Oops. I didn't mean right triangle, just solve the triangle. Now there is one situation where 1/2 base times height, we do have the base and the height. Does anybody remember what that scenario is? Jacob? If it's a right triangle, then the legs are the base and the height. Doesn't matter which one you make which. But if we have a generic triangle, the height is kind of hidden from us, right? So let's just say that we have the situation that we kind of identified earlier. So we'll make B the base, and we'll draw on this height here that I'm going to call H. Notice here that when we draw on that H, we get a right triangle. Since I have a right triangle, I can use Sohcahtoa inside that little right triangle. So I can say that sine of A is equal to opposite over hypotenuse. And if I multiply both sides by side C, I get that H is C times sine A. So if we now substitute this in, our B was side B, and our height is C times sine A. So this is a new version of our area formula that involves only the pieces of a triangle that we have solved for, right? Just side lengths and angle measures. No heights needed. That's pretty cool, right? Note that if this is a right triangle and angle A is the right angle, sine of 90 degrees is 1, so it just turns into 1/2 base times height, like it should. Everybody cool? Just to point out to you guys, if I go to use this area formula, I would prefer not to have to solve the entire triangle to be able to use this area formula. So if I really just need sides B, C, and angle A, what kind of scenario is this really best with? Side, angle, side, right? Now, if I don't have side, angle, side, like say I have angle, side, angle, or something like that, what do I have to do? I just have to solve it enough so that I can get another side length, so that I can do a side, angle, side somewhere. You know? Is that cool with you guys? So you don't have to solve the whole triangle, you just got to do enough of it so that you could do the area formula. Now, you could certainly solve the whole triangle if you wanted to. That's fine. Our other option, there's another version of this same area formula. It's called Heron's formula. And it says that the area is equal to the square root of S times S minus A times S minus B times S minus C, where S is the quantity A plus B plus C, all divided by 2. Sometimes we call that value S the semi-perimeter. Notice that A plus B plus C is the perimeter of our triangle. And half of something is often, we designate that with semi as the prefix, like half a circle is a semicircle. So. Now, I would think the obvious question is like, yo, Mr. Kulik, this does not look anything like the previous formula you gave me. How are you leading me to believe that this is really the same thing as the previous formula that we just like rearranged? Yep, that is what I'm asking you to believe. Fiddlesticks. So let's demonstrate how I can get this new Heron's formula from that previous one. What I'm about to do, is this something I would ever ask you to repeat? Nope. Is it something that I expect as we walk through it together you could follow what I'm doing? Yup. But not something I would ever ask you to do by yourself. Okay. So let's say that we have this previous area formula. I'm going to start by multiplying both sides by 4. And then I'm going to square both sides. Now I notice in here that I have a sine squared. If I think back to last semester, I had an identity there that I know sine squared is equal to 1 minus cosine squared. Right? That sound familiar? I'm going to apply that identity here. And then I'm just going to distribute that 4a squared b squared through to get rid of the parenthesis. Now, if I take a look what I've written here, this to me looks like a difference of 2 squares. I notice the first thing is something squared. And the second term there is also something squared. So conceivably, I could factor this now using a difference of 2 squares. But before I do that, I see something in here that I go, aha! This looks familiar. What does this look like? Yeah, it looks like part of the law of cosines, doesn't it? So if I take my law of cosines, I can add that 2ab cosine c over to one side, and then subtract the c squared to the other side. So I'm going to make that substitution here before I factor my difference of 2 squares. So now I'm going to factor. So that's going to be 2ab plus a squared plus b squared minus c squared times 2ab minus a squared plus b squared minus c squared. Everybody okay with that? I just factored it like a difference of 2 squares. I'm just going to now rearrange things a little bit. So I have a squared plus 2ab plus b squared minus c squared. And then in the other piece, I'm going to pull out the c squared. And then I'm going to have a squared, and I'm going to push into the parentheses this 2ab. everybody okay there? We good with why the sign on c squared's flipped? To move it out of the parentheses, I had to distribute the negative. And we're good with why the sign on 2ab switched. To push it into the parentheses, I had to multiply by a negative because there's a negative out front. Everybody's okay with that? Now you could have just distributed the negative through, rearranged things the way you wanted, and then refactored it. That would be okay to do too. I just didn't want to write all that down. The point here, though, is, oops, this. Do you guys recognize that? Those are both perfect square polynomials. So I can factor those. So that's going to be a plus b quantity squared. And then I still have my minus c squared. And then c squared minus a minus b quantity squared. Oops. I have an equal sign there that I didn't write. Everybody still going okay? If I look at these, what do I see again? More differences of two squares. Okay, so I'll factor each one of those. So that's going to be ab plus c squared, bless you, and then ab, oops, plus c, sorry, and then ab minus c, and then c plus a minus b, and then c minus a minus b. I'm now just going to distribute some things and then or rearrange the things in parentheses so that the little parentheses go away. Oops. What did I do here? This should be a plus c minus b. There we go. So far, so good? All right. What I'm going to do now, the first parenthesis, I'm not going to do anything to. The second parenthesis, I'm going to add in a c and then subtract a c right after that, which is equivalent to doing nothing. If I add c and then subtract c right after it, I haven't done anything. In the second parentheses, I'm going to add in a b and then subtract a b right after. And the last parentheses, I'm going to add in an a and subtract an a right after. Oops. Still got the minus a at the end. And it's okay to do that because if I add something and then subtract it right away afterwards, I haven't done anything at all, right? Just like adding 0. Now, the question you guys should be asking is, why in the world would you want to have done this? What did that get you? If I look inside of each parenthesis, I have an a plus b plus c in there, right? What is a plus b plus c? It's got to be 2s. Everybody see that? That a plus b plus c has to equal 2s? So I'm going to go ahead and make that substitution. Oh, Absolutely. Thank you, John. Okay. If I look at each one of these sets of parentheses, I notice there's a greatest common factor of 2. So I'm going to pull those factors off. If I look at that right-hand side, everything is being multiplied, right? I can multiply anything, or I can multiply in any order I want. So what I'm going to do is I'm going to move all the 2's to the front. And 2 times 2 times 2 times 2 is 16. And I'm just going to rearrange the parentheses so they're match the order that we see in our formula. I divide both sides by 16, so the 16s go away. And then we square root both sides, and bada boom, bada bing. There is Heron's formula. So, yep. I'm convinced now, Mr. Kulik, this is definitely the same thing as the previous formula. It's just a different version. Now, when would I want to use Heron's formula as opposed to the previous one? In a side situation. Yeah. Is that the only time I'd want to use Heron's formula? Yes. Because to get if I have to solve a triangle to get 3 sides, any solving of triangle, the last step was always solving a side length. So it would mean to use this, I'd have to solve the entire triangle, in which case I would have passed the side angle side where I could have used the previous formula at some point. So this formula just allows us to avoid having to solve an entire triangle. You know what I mean? It's just another little get out of jail free card. Okay. Let's go and do a couple of numeric examples. I'm pretty impressed this time. I remembered all of the steps for that Heron's proof without having to look at my notes this time. Notice back there in that proof of Heron's formula, we didn't use anything that you didn't already know, right? All we did was some factoring techniques from Algebra 2. We used the law of cosines and one-trig identity, both of which we already knew. Now, putting that all together to get where we're trying to go would have been very non-trivial for us. But the tools we needed were things that we all had access to. In a perfect world, you could have done that on your own, but this isn't a perfect world, so that's an unrealistic expectation. Okay. So let's say we want to find the area of the triangle described below. Well, just like I've done before in every other situation, I'm going to draw and label my triangle. What situation is this? Yep, it's side angle side.
They gave me a note.
Oh,
just in case.
Sure. Thanks, dude.
Yep.
And since it's side angle side, I can just plug this immediately into that formula. No modifications needed. And just type this into our calculator. 1/2 times 10 times 27 times sine 43 9207. Millimeters squared, since the unit was millimeters. And I'm done. Mr. Kulik, that was so fast. I know, man. Is there any way it could be longer than this? Well, if I gave you like an angle side angle situation, you might have to do a little bit of solve for something else before you could use the formula, but you know, you really just need to do law of sines once to get the other piece you would need, and you'd be good. It's not so bad. What if we do, say, this one, where we have side A is 5 meters, side B is 8 meters, and side C is 10 meters. Again, I'll start by drawing and labeling my picture. What scenario are we in here? Side, side, side. So what I need to do first?
Oh, solve for S.
Nope. Gotta do something before I do that.
Oh, shit.
Make sure it's a triangle. Right? Side, side, side doesn't guarantee that it's a triangle. What is the check for making sure it's a triangle?
Add up the sum of all its sides.
The sum of the legs has to be greater than the hypotenuse. So 5 plus 8 is greater than 10. So we definitely have a triangle. So we're good to go. Mr. Kulik, are you a sneaky enough jerk that you would like put a problem on the test or a quiz or something where like you ask me to find the area of something that doesn't exist? Yeah, I think that I would. Now that doesn't make me a sneaky jerk anymore, it just makes me sneaky since I told you that that's definitely something I would do. Right, so now you just have to be worried about it. Right, I'm aiming for sneaky, not jerk. All right, so there's my value for S. So now if I plug this into Heron's formula, 23 over 2 times 23 over 2 minus 5 times 23 over 2 minus 8 times 23 over 2 minus 10. This is a case where the ants function on your calculator is your friend. So I'm going to do square root of ants times ants minus 5 times ants minus 8 times ants minus 10. So I get 1981. So fast. Yeah, my dude's pretty fast. To do this problem without using the just 1/2 base times height, that's a royal pain in the butt. That takes you have to use the law of sines to get an angle measure, then you need to like dump it into that previous formula, which is a hassle compared to just plugging stuff into this one. But that's it for 7.4. That's all you really have are these two new formulas that are both real straightforward to use compared to the other ones. So at this point, you guys should be able to do 23 through 30. So we'll add that into your problem set for Sunday. What have we not done so far today? Homework quiz. Are we going to do the homework quiz today? No. So what should you expect next class? Homework quiz. What's it going to cover? First 3 would not cover areas, since we wouldn't have had a chance to talk about areas before we take the homework quiz. What's up?
We went over the areas
yourselves.
I mean, I'm telling you, I'm not going to do that.
What if we just had a quiz just on the area stuff? That would be easiest stuff.
Oh, you're a funny guy.
Oh, what's the test though?
The test, so next class we'll do the homework quiz and we'll review. The following class we'll take the test. So for you guys, that would be Wednesday next week, I think, because Monday's a day off.
Right.
So the A day is Wednesday, Friday next week. Cool? Absolutely. Oh my goodness.